and thank you for attending this presentation. My name is Justin Bressi, and I'm a Business Development Manager with Aerotech, a global precision automation company that is headquartered in Pittsburgh, Pennsylvania. For those of you who don't know Aerotech, we've been in business for over 50 years, specializing in producing automation technologies that enable extremely high precision and high throughput applications in a variety of industries, including the optical communications industry. Our long heritage in this industry has positioned us well to assist our customers in solving the challenges of manufacturing and testing the devices that enable modern data centers. Should you have any follow-up questions related to this presentation, or if you are looking for general automation guidance, please reach out to me via email or LinkedIn, or feel free to ask questions at the conclusion of this webinar. Industry shaping trends like AI and high-performance computing have been evolving at a breakneck pace, continuing to push the limits of how we interact with the digital world. As these technologies grow more powerful and more ubiquitous in our daily lives, they're driving an insatiable demand for additional computational power at hyperscale data centers, demands that are currently outpacing Moore's Law. And while headlines tend to focus on this growth in compute demand, the bandwidth needs for communicating information from one system to another within data centers is following a similar trajectory. As established technologies have begun to see diminishing returns and in some cases begin to reach the limitations of fundamental physics, many people have claimed that the traditional understanding of Moore's Law is quote-unquote dead, or at the very least, meaningfully slowing down. Because of this, large-scale deployment of paradigm-shifting technologies such as silicon photonics and advanced packaging will be necessary to meet the demands of applications like AI and high-performance computing. In today's webinar, we'll delve deeper into these technologies and discuss some of the key process challenges in manufacturing and testing them. Speaking of silicon photonics, this technology offers several distinct advantages when compared to traditional semiconductor-based electronic devices. First, bandwidth and latency. Optical signals have been a foundational communication technology for decades, enabling data transmission at significantly higher speeds and at greater bandwidths than electronics alone. Additionally, optical signals are more resistant to external interference, reducing signal attenuation, particularly over long distances. High-speed optical interconnects within data centers take advantage of these properties. The next benefit is energy efficiency. Optical technologies that more tightly integrate photonic components shorten the lengths of conductive copper on the device, reducing power draw and heat generation. This is particularly critical as the power demands of data centers are growing exponentially. Finally, device footprint. Adoption of silicon photonics technologies has allowed transceiver manufacturers to pack more functionality into a smaller space, increasing the density of optical interconnects. Additionally, while still in the early stages commercially, emerging technologies like co-packaged optics offer the promise of replacing the industry standard pluggable transceivers with more integrated devices that are far smaller in both size and power demands. Because of these advantages, optical transceivers utilizing silicon photonics-based photonic integrated circuits already make up a substantial portion of the optical transceiver market, particularly for the highest speed devices, and this share is consistently growing. Another important and related trend of the fundamental technologies of modern transceivers is the shift towards tighter integration at the package device level. Traditionally, the optical engine of the transceiver, which includes photonic integrated circuits and a light source, is housed within the pluggable transceiver itself, as shown in the top diagram. However, enabled by advanced packaging techniques such as heterogeneous integration, where components of different materials are packaged together, new architectures, including onboard optics and co-packaged optics, are being developed to continue reducing both the physical size and power demands of these devices. By shortening the electrical paths on the device, signal robustness is improved and electrical resistance is reduced, lowering the picojoules consumed per bit of data transferred. Tighter integration is driving significant advancements in optical transceivers, but the downside of these increasingly complex architectures is that this complexity also introduces new challenges in manufacturing, testing, and packaging. Perhaps the most demanding aspect of both manufacturing and testing optical transceivers is the need for extreme precision, often on the micrometer and even nanometer scale. To meet these stringent requirements, manufacturers often must invest in advanced equipment and processes, including high precision positioning stages. So what specific processes require these micrometer and nanometer levels of precision? While not an exhaustive list, I plan to cover a few today, including wafer and die level testing of photonic integrated circuits, which is often performed to ensure quality picks before device packaging takes place. Precision alignment for advanced packaging techniques, including heterogeneous integration and 2.5D and 3D chip stacking, and optical alignment and assembly, where components within a transceiver are aligned to ensure adequate signal strength. As you'll see on the subsequent slides, all these steps of the manufacturing utilize precision motion control systems in different and sometimes related ways. As I mentioned previously, silicon photonics wafers can be manufactured using traditional semiconductor methods, making silicon a very compelling option for photonic integrated circuits. Similar to traditional integrated circuits, both wafer and die-level testing methods are used for quality control, but testing PICs is a much different and more complex process than testing traditional electronic ICs. This is because testing photonic integrated circuits requires testing of both the electrical and optical paths on the die. For electrical paths, a simple physical connection is usually all that is needed to conduct a test. But for optical paths, devices are typically sensitive to the positioning of the probes rather than just contact. Because of this, precise probe manipulation is required, including in several degrees of freedom and in complex kinematic arrangements. As an example, shown here is a diagram representing edge coupling on a silicon photonic wafer. Precision, linear, and angular alignment between the probe and photonic device under test is required, as misalignments measured in micrometers and even nanometers can affect the signal loss during testing. Additionally, the adjustments made during these tests typically need to occur at the tip of the probe, so a system capable of pivoting about this point of interest is often needed. So how are these precision alignments executed? High precision positioning systems, such as the 6-axis direct drive Aerotech solution shown here, enable highly accurate placement of the optical probes to ensure consistent and repeatable device testing. Combined with Aerotech's Automation 1 motion control software and drive electronics, this system is able to pivot several degrees of freedom about the assigned work point and achieve off-axis error motions measured in single-digit micrometers, despite the work point being hundreds of millimeters from the probe's mounting point. Automation 1 simplifies configuration of these work point offsets, eliminating the need for the user to perform complex linear algebra. Additionally, alignment applications like this also typically take advantage of Automation 1's optical alignment algorithms to optimize the position of the probe based on an optical signal strength reading that is sent to the controller. The controller uses this signal strength to adjust the position of the system based on several built-in algorithms, identifying the ideal position for the probe to maximize the signal. Meeting stringent test requirements like these often require careful selection of an appropriate motion system, whether the system is a serial kinematic system like the one shown here, or a parallel kinematic system such as a hexapod. There are several advantages and disadvantages associated with both technologies, but one key advantage of serial kinematics is that the off-axis error motions introduced throughout the range of travel of each axis are much easier to characterize and therefore calibrate. This improves the repeatability performance of the system and reduces the risks of unexpected 3D error motions. To get a bit more specific, the 6-axis serial kinematic positioner shown here includes 3 degrees of freedom in each linear direction, as well as 3 degrees of freedom in each rotational direction, roll, pitch, and yaw. This system utilizes non-contact motors and high life cycle cross-roller bearings to ensure the industrial robustness and high stiffness, while also minimizing 3D geometric errors, capable of achieving 10 nanometer steps at the work point offset as shown in the plot, which was captured using a capacitive probe. This system's single-digit nanometer level in-position stability and minimum incremental motion are highly suitable for wafer probing applications. Next, I wanted to touch on advanced packaging, a key set of technologies that are enabling not only the next generation of semiconductor devices, but photonics-enabled devices as well. Advanced packaging encompasses a variety of manufacturing methods being developed and deployed primarily by the semiconductor industry, some of which, like TSMC's CoWoS, have been fully commercialized for years. Many others, like 3D stacking and hybrid bonding, are in various stages of development and commercialization, with expectations of broader utilization in the coming years. Advanced packaging methods like heterogeneous integration, which combine multiple chips of different materials into one package, are critical to the pursuit of more tightly integrated optical devices mentioned previously. This is because the material properties of silicon prevent it from lasing, so for an evolving technology like co-packaged optics to truly integrate the laser source into the packaged device, non-silicon materials will be needed to be incorporated. Regardless of the materials being integrated, as the feature sizes of these devices push into the low single-digit micrometer ranges, such as in the case of hybrid bonding, the alignment accuracies required during the integration process continue to tighten well into the nanometer levels. Various 2.5D and 3D stacking methods are being used for heterogeneous integration. While the specifics of each process vary and different manufacturers use different and often proprietary methods, these processes almost always require precision alignment at some point given the size of the components being integrated. For example, when aligning chips to an interposer for 2.5D stacking, individual chips are stacked onto an interposer, and the microbump contacts and through-silicon vias of the chip must align with the redistribution layer within the interposer to enable connections to other chips in the package. These types of alignments require precise linear positioning of each chip in the X and Y directions, followed by motion in the Z direction that is closely controlled for both position and force. For wafer-to-wafer processes, additional challenges are introduced as the angular positioning of the wafer becomes even more important than during a chip scale process. For example, for a 300 millimeter wafer, if the wafer is rotated about the vertical axis by even as much as 1/100th of a degree, this results in a linear misalignment at the edge of the wafer that's larger than 25 microns, and misalignments of this magnitude will result in significant defects and therefore reduce yield. As would be expected for any high-volume manufacturing operation, and especially so in the semiconductor industry, both high yield and high throughput are critical, so high-performance positioning systems that can combine the necessary precision with high dynamics are foundational to an optimized process flow. As mentioned previously, heterogeneous integration is required for co-packaging of optics onto a single substrate. Just recently, a major manufacturer of optical communications equipment debuted one of the first commercially available products that takes advantage of this technology, an optical switch that utilizes fan-out wafer-level packaging to co-package photonic integrated circuits with traditional ICs. However, scalability of these processes remains a key challenge for the industry, as many of the current approaches require aligning and stacking chips individually, which is highly time-consuming and therefore throughput limiting compared to most traditional semiconductor processes. Because of these limitations, new parallel processing methods are constantly being explored to reduce costs and increase output. One parallel processing method that is being explored at the lab level for heterogeneous integration is microtransfer printing. Microtransfer printing is a process that has been developed primarily for the production of another emerging technology, micro-LED displays. Microtransfer printing involves the transfer and attachment of an array of components simultaneously in a wafer-to-wafer format, typically. Since the wafer substrates can be different materials, microtransfer printing is a technology of interest for heterogeneous integration at scale. That being said, this wafer-to-wafer process is subject to the precision alignment challenges mentioned previously, and therefore require highly precise positioning equipment, like the example shown on the bottom right, for execution. This system utilizes an Aerotech planar air-bearing XY stage and includes a total of 10 axes of motion for conducting planarity-sensitive alignments between the various components. The exceptional geometric performance and dynamic capabilities of the air-bearing stage enable in-spec alignments to be achieved at high speeds, satisfying the throughput requirements of this specific process. After the chip-scale packaging processes are completed, the final assembly of optical communication devices often requires high-precision alignments as well. Even though the feature sizes are often larger than at the chip packaging stage, precision positioning in several degrees of freedom is critical to reducing insertion losses, very similar to the positioning challenges discussed during the wafer and die level testing section. Misalignments during the final assembly can result in devices that do not meet quality and signal specifications. As an example, the plot on the bottom right shows optical signal strength during an alignment across a 20 micrometer by 20 micrometer range. And as you can see, the signal drops off considerably with just a few microns of misalignment. Fortunately, alignment algorithms like the one in Aerotech's Automation 1 controller are purpose-built to solve these challenges. Additionally, closed-loop position and force control is often necessary during these bonding processes, as parts can shift due to epoxy-carrying temperature fluctuation and other factors. In the case of some types of optical devices, aligning multiple components simultaneously can also be necessary. Shown here is a solution from Aerotech that was for a specific optical device manufacturing application. In the case of this system, two separate optical components needed to be aligned at once, each with 6 degrees of freedom positioning flexibility. To accomplish this, Aerotech mounted two separate 6-DOF positioners in an inverted arrangement onto one of our linear motor-based gantry systems, all being synchronously controlled within a single instance of Automation 1. The linear motor technology enables the system to achieve high dynamics while moving between different devices, shortening the device-to-device travel time while maintaining micron-level positioning repeatability. Once in position, the 6-DOF positioners are able to align the components as needed using the Tool Center Point programming tool highlighted in the animation. Once aligned, high bandwidth closed-loop force control across multiple degrees of freedom ensures the appropriate forces are applied during the final assembly process. As you can see, automation solutions like this one require the deployment of complex, high-precision mechanics combined with advanced control features, which are among our favorite kinds of projects at Aerotech. To summarize, I hope it's now clear that precision automation plays a critical role in the manufacturing and testing of today's modern data infrastructure. Demand for bandwidth within data centers is increasing exponentially due to technologies like AI, a trend that shows no sign of slowing down. With traditional technology starting to encroach on the boundaries of fundamental physics, innovations in paradigm-shifting technologies like silicon photonics and co-packaged optics will be needed to address these demands. Precision motion control already plays an important role in the manufacturing and testing of these technologies, a role that is set to become even more critical as optical devices become more integrated. Thank you for your time and attention today. Please feel free to contact me on LinkedIn or via email at jbressi.com if you'd like to arrange a follow-up discussion. My colleagues, William Ye and Simon Chen from our Aerotech Taiwan team, will now take some time to address questions from the audience.